Well, hello there. This lesson is going to be about Unit 5, which talks about reaction diagrams. So this is going to be pretty well all theory. I know you don't like that, but we have to go through the motions. So, reaction diagrams. First thing I want to talk about is the activated complex. You know already that when we have reactants that collide together, eventually they form products. Does this happen in one shot? No, of course not. We have what we call in between an activated complex. So really what's happening is that your reactants are playing bowling together, or they're playing bumper cars rather. So they're colliding with each other, and when they collide with the right amount of speed, right amount of energy, and at the right angle, they actually disconnect from each other. So they break their bonds. And then we have what we call the activated complex, which is just a bunch of random atoms that are not attached together anymore. Now this is highly unstable, it's highly energetic and therefore highly unstable. The atoms don't like to be that energized. So what do? They release some of that energy while they form new bonds to get a little bit more stable and a little less energized. And we obtain what we call products. So point number one today, what is the activated complex? It's the step in between the reactants and the products, whereby the atoms are more or less separate, very energized, and ready to form new bonds and release that extra energy that they don't want. So this is very brief. We actually don't really observe this stage, but we pretend, we suppose that it's there. Now, another thing that is important to know is that reactions don't occur on their own like that. It's not because I look at a piece of paper that it's going to catch on fire, for example. I don't have laser eyes and I don't do magic. So we need what we call a certain amount of energy to start a reaction. We call this the activation energy. So that activation energy is the minimum quantity of energy that a reaction needs to start. If we look at the lighter here, in order to create a flame, it's not just by opening the cap that the flame will appear. No, the lady would need to turn that little roulette here, which will cause friction, and that friction will cause a spark that will start the combustion and will allow for the flame to appear. So that friction gives just enough energy to start the actual combustion. And that little amount of energy that begins the combustion is called activation energy. Another example would be to compare the activation energy to a barrier that the reactants need to cross. If they don't have enough energy, they won't be able to get to the other side of the reaction where the products are. So if we look at the roller coaster here, we can see the people are going down the hill, but before they were going down that hill, they had to come up on this side. If the roller coaster doesn't have enough energy to go all the way up, what's going to happen? Well, yeah, the roller coaster is going to go back down. The same way the reactants, if they collide with some energy that's not sufficient, will go back to their original stage of being reactants. And then when they collide again, if they have enough energy, they'll be able to go all the way up to the top where the activated complex is. So at the top we have a very energized situation where the activated complex is. And once they can attain that energized state, they can go to the other side and go down like the roller coaster and become products. So if you think about your graph from last time, when we were talking about bonds broken and bonds formed, well, we have, in this case, I'm just going to draw it on this side, even if it's the reverse way from the roller coaster. Let's pretend my reactants are here. Well, my reactants would gain energy and break their bonds. They would attain the plateau that we now call activated complex, where all the atoms are scattered. And those atoms that are very energized then lose energy while forming bonds to become more stable and become the products. So that's it for my roller coaster example. If we look at a real graph, we'll have the following. So we have the same thing here. We have the reactants and we have the products. How did they go from one to the other? Well, the reactants had to gain a certain amount of energy, break their bonds, attain the activated complex where all the atoms are scattered, very energized. As you can see, it's higher up on the energy scale. And then those atoms would form new bonds and release some of that extra energy that they don't want, that's making them unstable. Now we give a name to this amount of energy needed to start the reaction. We said it before, it's called activation energy, or EA, activation energy. So the activation energy is always the amount of energy that my reactants need in order to attain the activated complex stage. So this amount of energy from the reactants end to the top of the hill, and which is also equivalent to the amount of energy of the bonds broken. It's one and the same, basically. And then we have the bonds formed, and the difference between both, as you learned in a previous lesson, gives you the delta H of the reaction, the overall amount of energy involved in the reaction, or the overall change of energy within the reaction. So this is for an endothermic reaction. Now, if we look at the exothermic reaction, so for the exothermic reaction, we have bonds broken, or also the activation energy. And then, so with that amount of energy the reactants are gaining, they can attain the activated complex, which is the highest or most energized part of the reaction. And then those scattered atoms form bonds, release their extra energy to form the energy levels, or to attain the energy levels of the products. Okay, so here we have three graphs. If you observe the blue one doesn't really have an activation energy per se. It looks as if it's just going from reactants directly to products. This would be what we call a spontaneous reaction. So the activation energy is 0. Basically what it is that there's enough energy in the environment to allow the reactants to turn into products on their own. We don't have to supply an extra amount of energy to break the bonds. So there's no activation energy per se. That energy comes directly from the environment. It's already available to the reactants. An example would be a piece of ice that you're holding in your hand. You don't have to take out the blowtorch, let's say, to melt the piece of ice. The piece of ice will melt on its own because it's taking heat from your hand and from the environment, allowing it to melt, so drawing energy from the environment. So it has no activation energy. So anything that happens without the help of an extra energy source would be called a spontaneous reaction. And most often it's the air, the environment, that will provide that extra energy necessary for the reactants to react together and become the product. So the air or the environment will provide energy, sufficient energy to allow for spontaneous reactions. Okay, what do we do mathematically with this? Well, if you understand all the vocabulary or concepts, you'll understand the following. It's not very complicated. So it says, plot a diagram of a reaction between methane and sulfur, which reacts according to the following equation. The activation energy of this reaction is 140. So we know that from the bottom here, where the reactants are, to the top here, there has to be a value or a difference of 140 kilojoules per mole. The enthalpy change is 14. So they're telling you that the delta H is 14. So between the reactants and the products, there has to be a difference of 14. So they just want you to plot it. They're not giving you what the enthalpy of the reactants is, nor for the product. So you can't put a value here. You can't put the values. The only thing you can do is draw a line for the reactants. Because your delta H is positive, you know it's going to be an endothermic reaction. So your products have to be higher up than your reactants on the graph because it's a positive value of delta H. It's endothermic. And so you're going to show this value because it's given to you in the question. You're going to draw the proper graph, an endothermic graph, and you're going to put the value of the activation energy, which is also given to you. So those are the 4 points that you must put. There's another thing you have to put. It's the reactants per se. So because your reaction is given to you, you know that these are your reactants. You must write them on the line that represents the reactants, as well as write the products on the line that represents the products, because you know what their identities are, you know what the substances are, and label what where your activated complex is. So those are the different things that you must put on your graph. The last thing is, don't forget to label your axis, so potential energy here. If you put enthalpy, it's fine. If you just put energy, it's fine as well. but always put your units, kilojoules per mole. And this is time or progress of the reaction. Time would be good as well. So these are the different points that must appear on a graph if you get a question like this. Last item, reversible versus irreversible reactions. So some we can turn back, like physical changes. Water can evaporate or it can condense. I can melt a piece of ice, I can freeze the water back, so that's reversible. Irreversible, something that burns, for example, so I can't unburn a piece of wood. Because something can be sometimes reversible, we're going to have two graphs. We're going to have the forward reaction, which would be, for example, to melt something. So my reactants will be colder, will have less energy than my product, which is now, let's say this is a piece of ice. So my piece of ice is very cold, has little energy. My water, liquid water, will have more energy here because it's in the liquid form. So this would be one reaction. If I take that same water, as you can see, the amount of energy is equivalent because my products become my reactants in this case. They should have, my products for the forward reaction should have the same energy as my reactants for the reverse reaction. Here they label them products and products just to show you it's the same substance. But in this case, my products really become the reactants of the second reaction. So this substance here then loses energy to give me the end result, right? And the end result, which is exactly the same as what I had initially here, well, both should have the exact same amount of energy when I compare as well. So these two should have the same amount of energy. These two should have the same amount of energy, and they do. So I end up with a mirror image. The two graphs are mirror images of each other. My two delta H's have the same value, but of opposite signs. This one is a positive delta H, this one is a negative delta H, but the actual value will be the same. So I might have here plus 50 kilojoules per mole, here I'll have minus 50 kilojoules per mole. Because they're mirror images of each other, they have the same value, different sign. Now, you have this if something is reversible. In the case of a wood that burns, you wouldn't have the reverse reaction because you can't unburn the piece of wood. So you only have this forward versus reverse when you have something that is reversible. Another point I want to make, because the activation energy is always the difference of energy between the reactants and the activated complex, in the case of an endothermic reaction, you can see that the activation energy will normally be larger than for the reverse reaction, whereby the products are becoming reactants. The top of the hill is much closer from here to here than from here to here. So your two activation energies will be different. Your heats of reaction will be the same, opposite signs, but your activation energies will differ from one graph to the next, from the forward to the reverse. So what do they have in common? Same heat of reaction, absolute value. So yes, one is positive, one is negative, but the value per se is the same. What they don't have in common, the activation energies are not the same. Now, as a general rule, reversible reactions have a smaller enthalpy change. What I mean by this, if I compare the following, 4, I will look at my delta H. This has a large delta H, or these two, this pair, has a large delta H, have a large delta H. This pair has a smaller delta H. So if I had to choose between the two, which one is reversible, it would be this one, because the delta H's are smaller than these two. So the larger the delta H, the less likely the reaction will be reversible. So this one would probably not be reversible. This one would probably be if I had to pick. For a reversible reaction, we put a double arrow. For a non-reversible, we put a single arrow going forward. That's the difference when we write the chemical reaction equations. And that's it for that. That was your Unit 5 lesson. Ciao!